It's my pleasure to introduce for the third talk of today, Peter Cholak, who will speak to us about Ramsey-like theorems on the rationals and the Rado graph.
So thank you, Linda. Thank you, Elvira and Paul, for inviting me. And thanks everybody for listening ahead of time. So I appreciate everybody being here. Well, I'm just going to go to the talk. So this is a survey talk about countable structures that have big Ramsey degrees. So I'm going to explain what that is in a bit. Okay. And I'm going to try to highlight connections to computability and reverse mathematics as I go along. And parts of this talk, instead of a little star about the theorems, are suggestive. Okay. So I haven't written them down, or we haven't written them down, or they maybe don't need to be written down, but they're suggestive of what would happen. And so the viewpoint's mine. The errors included are mine. Any mistakes are mine. And I have been somewhat neglectful about including full references, but I will say that a lot of this is reflected in a joint paper with Paul Elliott, Demir, Benoit, and Ludovic, which is on the archive and should appear eventually, and also draws heavily from work and discussions with Natasha Denbridden and Andy Zucker. So that's that. Okay, so let's go into it. So I'm going to fix a countable structure A. So some nice examples of the countable structures I want to fix are just the natural numbers. Okay, so there's no language there at all. So also I want to fix, say, the rationals. So I have an linear order there. And the rest of the things I want to fix are graphs. And there's several types of graphs I want to consider. There's a Rado graph. The Rado graph is basically if you have a pair of vertices, whether it's random, whether you have an edge between those nodes or not. And there's more. I'm not going to define these objects too much as we go forward. Okay. I mean, there is a definition, it's a little bit. There's also, I want to talk about the triangle-free Henson graph. So that's H3. So that just means that it's a graph, but any three nodes you pick do never form a triangle. There's no triangles. You can get the click tree, so, if you take K nodes, none of them are connected. And then you can do the same thing. If you just take a graph G, you can look at the Henson graph that avoids G. So I'm not going to, we'll talk about how to build these objects in a little bit, but I'm just going to take these objects as given. And certainly the naturals, the rational, and the Rado are well understood. And so all these are the properties they want. They're homogeneous, universal, countable structures in a finite relational language. Okay, so it's actually one relational language. Okay, so what does it mean to be each of these things? So homogeneous here means that countable structure A is homogeneous in the sense if I take any two isomorphic substructures of A, there's an isomorphism. That isomorphism can be extended to an automorphism. Okay, and so most of the time, it's effective. It's effectively extended in all the cases that we're considering here. Okay, so that's great. Okay, so by the way, ask questions as we go along. Okay, so universal. So this is the definition that I'm going to use of universal. So it's got to be universal for some class K. So we're going to fix some collection of finite structures in some finite relational language. Okay, I don't want to use. You could use constant symbols necessarily here, but I want to just that's just one area. Right, relational language. Okay, but all right, and actually you can use functions too, but I want the substructures to be closed under the function. But anyway, so the examples that we have that are related to it, they have all finite sets is one class. Okay, so everything's finite, by the way. All linear ordered sets. Okay, all finite graphs, all triangle free graphs. All K-click free graphs. And if I fix some finite graph, all graphs that avoid that graph as a subgraph, right? So, an isomorphic copy of that. Those are examples. Okay, and they correspond to my earlier examples. So A, the structure A is universal for K. What do we have to have? Every finite structure of A is in K. And you go back and think about that. That's certainly the case of all the structures I had before. Okay, now I wrote this differently than people might see it other places. For every finite structure C of A, and every B in K extending C. Okay, so you have, so C might be inside of A, but B might be sticking outside of A. Okay, there's an isomorphism of B into B hat that's inside of A. So maybe a picture here is good. So if this is A, and then there's your C here, and then your A extends out here, you could get a copy inside. Okay, so even who knows what A and B look like, you could always push it inside of A. Okay, and so so basically the theorem is missing, and it's actually, in some sense from Henson's work earlier about the click-free graph existing, that these objects exist. So all the objects that I talked about are homogeneous and universal for this corresponding collection K. And this actually gives you, I'm not going to go through this proof, but this actually gives you a way to construct these objects. You just kind of take a product. I'm not going to talk about what kind of product, but you take a product of all these finite structures, and that gives you that infinite structure. And that construction, well, we're not going to talk about it too much here, but that construction, it's easy how to do it in finite sets. You just kind of take the union of all finite sets. It's going to be what you want, right? But it works in everything other construction. Okay, so something to be explored about how effective that might be. Okay, but it is effective. Okay, so I want to draw a picture of what the possible B's could be. All right, so I want to start with the natural numbers. So there's the set, and so this is the size 1, 2, and 3. That's 2. And there's 3. Okay, so just want to point out, right, that we have, if you're looking at structures of size 3, you get 3 elements. And what about for the rationals, right? You get, again, a point for everything. You always, for a singleton, you just get 1 point because they don't have a function, right? So there's always, for looking at B, the size 1, it's just a point. For the rationals, they're ordered, so 1 is less than the other, right? What about for the Rado graph? Well, you have basically things that are connected, or they're just, they're connected by an edge. Okay, with the rationals, you have basically 3 points like that. They're linear, right? Any 3 points you have, if you pick them out, they're going to be linear ordered, right? For the Rado graph, you could have 3 disconnected points, 3 points with a vertex. You could have, or you could have 3 like that. So you get basically those 3 objects. They're all going to be isomorphic to each other. Those are the objects you get. Oh, thank you. Yes. All right. And then I'm not going to do this for now. If you look at K3, right, everything is the same except this one here. I'm going to change the color here, is out. Oh, failure. All right. So I just want to remind you what those things look like. Okay. So, all right. All right. So what I want to do is, so now let's see what we're going to do here. I want to color isomorphic copies of B in our structure A. So we're going to let A over B be all the isomorphic copies of B in A. Okay. And so, well, we have this notation, basically A, well, I'm not going to read it. This means that for every coloring of the copies of B and A into K colors, there is an isomorphic structure. So, I'm going to read it like this. So, here we go. So, I basically color all copies of A. In A, I color all copies of B. Okay, this is the wrong point. So I'm coloring all copies of A the color B. I want my pointer. So in A, I color all copies of B, and then with K colors. And then what happens is that I get an isomorphic copy A prime. This is where the A prime here comes from, such that basically, if I look at the copies of A prime all the copies of B, I only use L colors. Okay, and then I want to say that L is tight if there's a coloring where I have to use exactly. I can't get away with fewer colors. Okay. Yes. What's that? No, it's what it means is that the object I want to get, the quote homogeneous object, needs to be isomorphic to A. Okay, so it doesn't have to be, it has to be isomorphic to A. So that's what these guys here are, isomorphic. Okay. So this is what you're coloring, and this is, you want to get a structure that looks like that else. Yep. Yes, A is always, so we fixed A ahead, right? Yes. I mean, we'll use a little notation. Do you have a question, Linda? Oh,
For
I'm
the
sorry.
online participants.
Okay. Okay, so then so an example of this is Ramsey's theorem, which says basically if I take the naturals, and I wrote this Bn is just basically the finite subset of size n, and I color all the finite subsets of size n. There's a copy of the naturals, so there's an infinite homogeneous set where basically I have one color. Okay, so that's an example of that use of notation, right? And I should mention, I think Ramsey spent his life in Cambridge, so it's kind of nice to be back here where Ramsey spent his time. And so, yeah. So someone told us yesterday where Wittgenstein was buried, and I think that Ramsey's in the same cemetery up the hill someplace. Yeah, yeah. Okay. And so I mean, we're logicians, and Ramsey proved this theorem and tried to find some decision problem for in basically first order logic, which is undecidable. Well, a fragment of first order logic, which is undecidable, right? Okay, so now you have to be really careful about Ramsey's theorem because it suggests incorrectly that a tight bound will always be 1. Okay, but this is for the structure that we're considering. This is not the case unless we're in the naturals, or the structure has size 1. Okay, the B has size 1. Okay, so we need not get a tight bound that's 1. So okay, so what does it mean for a structure to have big finite degrees? So for a finite structure B has finite Ramsey degree in A. This should be big in there. I'm sorry. So it has finite Ramsey degree in A. If for some L, there's a coloring where I get it, so in other words, I always get a coloring that I can always reduce it that number of colors. Okay, a copy. Okay, L is tight. If L is tight, we say that B has exactly big Ramsey degree L. Okay, and then a structure A has finite big Ramsey degree if for every finite substructure B of A, it has finite big Ramsey degree. Okay, and it's a theorem that all the structures that I've considered have finite big Ramsey degree. Okay, and moreover, for every finite structure B of A, there's a tight bound L sub B. Okay, and so I included Ramsey, the original Ramsey, on this because obviously he did it for the nationals, right? And this is a starting point, but also I'm going to credit Natasha Brennan for a lot of this, but there are other people certainly involved as the structures get more and more complicated. And I should be careful because I neglected people. There's Devlin who did this for the rationals. There's Sauter and Gene Larson and others and Tovacevic who did it for the Rado graph and things like this. So I've neglected a lot of people in this. And I should have said, instead of neglected, I should have said missing. I apologize. What? Okay. Who? Okay. So missing. All right. Okay. Okay. So I wanted to point out, I mean, so I'm looking at this from computability viewpoint, right? And so I'm kind of looking at how complicated these theorems are. Okay, and so all these results imply Ramsey's original theorem. So in other words, I have to be careful about the instances that I'm talking about. So I'm not going to be very specific, but if I fix B of size n, that applies Ramsey's theorem for that corresponding n. Okay, so there's something to say interesting in computability theory here. And so we'll get to that as we go on. Okay. So I want to at least explain why it's called big versus small. Okay. And so K, the finite class of collections now has small finite degree if for every structure A and B in K, there's some larger C such that if I inside C, I copy colors of B, I could find a copy of A where the copies of B only involve L colors. Okay, so it's the same thing somewhat. Okay, and so again, finite Ramsey theorem is a great example, and that of course is what Ramsey wanted to do, right? And so Ramsey got basically the infinite version implies a finite version. And so that doesn't work out that using compactness, and that doesn't work out as nicely to use to prove this in this case here. But all these structures here have a small Ramsey degree. Okay, and I put some references is down there. Okay, and I shouldn't have said perhaps. I said it should be. I'll fix these slides and others. Okay, and so all these corresponding things have small Ramsey degree, and of course, if we could, we'd love to understand tight bounds. In other words, if I gave you the size of A and B, what's the size of C should be, right? And of course, there's multiple. If C has size 100, there might be many structures of size 100 that are non-isomorphic to each other, right? In this language, so there's a lot to be known here. Okay, and so it's still open to work out this precise connection in different classes between big and small, right? In terms of, I mean, certainly with the naturals, it's compactness gives it to you, but it doesn't happen here. Okay, so all right. Okay, I'll slow down. All right, so I want to give an example here. So I want to look at what I'm going to do is look at some specific colorings for a little bit and see what happens. And so this example is from, how do you pronounce this? Proskinsky, right? I mean, okay. Thank you. All right, so I'm going to look at the rationals. And I'm going to color pairs of rationals. All right, so I'm going to just color pairs of rationals. And so I'm going to consider the rationals. I'm allowed to pick any copy of the rationals that I want. So I'm going to pick the rationals as the dyadics. All right, the dyadics are certainly fine, right? And so I picked the concrete coding of dyadics there, right? So from -1 to 1 ordered as normal. Okay, so it's basically I've got it coded as a tree. Okay, in that sense here, and then I'm going to color. I'm going to color the pair 1. It should be. I made some mistakes here. I want to color the pair Q sigma tau sigma 1 if the length of sigma, if the sigma is less than, if sigma is smaller than tau in the tree, and the one's less than the other, and 0 otherwise. All right. And now what I claim here is that in any subcopy of Q, so if I have this tree in some sense, or I have this copy of the dyadic, so I take another copy of the rationals inside there, I claim I have to have both colors appearing, right? Because what happens is, if I have both colors, right, I have some node in that tree, right? I have to have something above it that's less than it, and something above it that's greater than it, right? And those give me two different colors, right? Because there's only finally many nodes below it, right? So I have to have those two colors appear, and also. I'm not going to go through this, but there has to be pairs of each color where the gap. If I have a node, if I have something here, I know I have to have something bigger than it, but the gap could be very, very large in terms of the lengths of the strings. Okay, both directions, and we could prove that. Okay, so when I say arbitrary large, I mean you pick some natural number, and I just have to give you a number bigger than that. Okay. All right, great. Okay, so this example suggests, I'm not going to count things, but this example suggests that the number of realized types of a B within A in an extended language, I haven't even know what that language is, but so there is some extended language, provides a lower bound on the big Ramsey degree of B and A. Okay, so in other words, somehow there's a larger language that I could augment my structure with, that basically if I look at B in that language, there's a corresponding model theoretic type that determines, right, the in an upper bound, well, sorry, a lower bound on the number of Ramsey degrees we have. Okay, so each type has to appear, right? So there's some kind of larger extended language, and then that somehow is there, right? That includes the enumeration, right? And that type tells me lower bound on the big Ramsey degree. Okay, but now of course I have to shrink it down to that if I can, right? I don't know anything about that, but I mean that makes sense. Linda, you have a question? So no.
What would be the language in the example that you're just doing?
So one thing I'd have to add is what's the language? I need to add in something that says, well, I'm going to add it in a bit, right? But with the previous one, I needed to say that one had a longer representation than the other. Right. So in other words, if I add in the fact that if I code in this fact here somehow. All right, so something about the enumeration. Right now, I don't, and so I'm going to leave it blank what the language, the extended language should look like as we move forward. And I'll give some suggestions, right? And so I don't know all the I don't know. Again, remember this is suggestive, right? So in some of the examples, I know the language completely, and the other ones, it's still suggestive. Okay, but we have to include the enumeration. Okay. Okay, but this number, okay, so but this example I gave tells you that the big Ramsey degree of pairs this tells you that the big Ramsey degree of pairs in the rationals is 2 or better. Okay, it doesn't tell you that it's 2. Okay, so how do you get it down to 2? All right, so so in some sense, this is what I wanted to add in there. I didn't want to be concrete about it. So all of the structures are basically countable. So for what we're doing here is we're going to think about them as enumerated by some nice, and I'll give some description of what a nice collection of nodes are. Right, so generally nice means an anti-chain under string inclusion. I want to have, say, one string of each length, and I want somehow this to be isomorphic to 2 less than omega. Right, so I'm going to pick out very nicely some trees. So basically, when I say isomorphic to 2 less than omega, I have to have an ordering on the nodes that basically duplicates inclusion, but it's not inclusion because I want it to be an anti-chain. So I'm very effectively picking out nodes that have this copy. So I am not going to go through the process of doing this, but you could do this carefully, picking out things that give you this representation. Okay, and it's actually hard. I mean, there's something going on here that's. I mean, I have to do this and do some other things. Okay, and then in some of the recent proofs, when we talk about the click-free graphs and stuff like that, we might have to use some finite labels on the nodes. So that would be added to the language. Right now, whether that's, I mean, I haven't completely explored those, whether that's necessary or not, I don't know. Right, so we're still looking at that. Okay, so I have this enumeration, and now, so here's a sketch of 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 a sketch that basically that B has finite Ramsey degree in A. Okay, so we have our nice enumeration of A. Okay, whatever we've chosen, and now we color it. And now because we have our collection of nodes is isomorphic to 2 less than omega, we have a coloring of 2 less than omega. Okay, and now I'm not going to tell you what Milliken's theorem is. It's a theorem that says if I have coloring of trees, I could get subtrees that have nice colorings. In other words, it's like Ramsey's theorem, but just for trees. Okay, so it doesn't, the actual theorem doesn't matter too much, but it basically, I could apply an instance of Milliken's theorem or some recent extension, we'll talk about it in a second, to get a nicely colored copy of 2 less than omega. Okay, and I have to do that each time for 2 less than omega. So at the end, I get basically a nicely colored copy of 2 less than omega that has all the colors that I want to have on it. And then I pull that back to A prime, and that, I mean, if I've done everything right, that if I have to do everything right, that should be give me a copy of A prime. Okay, that's what has to happen, right? So it's complicated. So I have to make sure that when I get everything together, that works out. Okay, so that's a sketch of a sketch of a sketch of a sketch of what's going on here. So there's a lot of stuff going on in there, right? So and now at the same time, you have to understand the number of realized types of B within every isomorphic substructure of A prime in our extended language. So I have this, I have this object here coded like this, and now I have to look at, hey, what are the possible if I have a substructure of this, a isomorphic A, what do they look like? And I have to be able to count all the number of types that I have in there. Okay, and if I'm lucky, the number of applications I need of Milliken's theorem and the number of types are the same. Okay, so I have to basically have a really nice representation here, right, that allows me to, to apply Milliken's theorems that number of times, but also I can count the types and I get what I need to have happen. Okay, and so I consider these proofs of total force, right? They're very difficult. Right, there's a lot of things to balance, right? How do you represent the things? How do you make the right types? What's the right language? Right, everything like that, right? So, and it's not so easy, okay? And they're difficult. This is just again, a sketch of a sketch of a sketch of a sketch of a proof, okay? And there is no kind of general proof of all these things here because, well, you don't need to do this for Ramsey's theorem. But you do need to do this for when you just look at the rationals or the Rado graph. And there's as you move from one to the other, there's a degree of complication. And then if you move to the click-free graph, there's another degree of complication that we haven't really looked at completely, in the sense that you can't use Milliken's theorem there. You have to use some kind of extension of Milliken's theorem. Okay, so and we don't really know everything to know about that extension of Milliken's theorem, right? So we don't know. Okay, and that's where Natasha Brennan comes in, because she proved this for the graphs, and that technique has been expanded to the other graphs. Okay, so that makes some sense. Okay. Okay. So how do I want to look at this? I want to look at this computability theoretically. And so we are going to fix some coloring of all the copies of B and A. And our goal is to find an isomorphic substructure A prime of A, where the number of colors used is just L sub B. Okay. And so we want to know basically where does A prime live in the arithmetic hierarchy, and if so, where? And so I'm assuming basically relative to the oracle. Okay. I mean, the coloring relative to the copy of A, right? They could be computable for all we care, or arithmetic or whatever. Okay. But where does it live relative to those things? That's what I want to answer, or try to answer, right? So that's what I want to try to do. Okay. All right. So the first case, when B is a singleton. So here it's just a domain coloring, right? So we're just coloring the nodes. Okay. And so, well, I didn't go through this, but A itself can be basically put together as a limit of finite structures. And I could just kind of group together finite structures that have the same color to get a copy of A. Okay. And so so if you go back to the original way that I was able to get each of these structures effectively, that process should be effective. I mean, so certainly it's the case for the rationals, and the Rado graph. Okay, so it hasn't been necessarily checked on the other ones, right? But you just try to put it together. You keep on extending each color to try to get a copy of A. And if you can't extend one color, well, just drop that color. You're left with another copy of A, right? And then you just kind of repeat until you get down to one color. Okay, so it's not done. It kind of mirrors the proof of basically the pigeonhole principle. Okay, and it's not done effectively. I mean, well, it's not doing uniform and computable. Okay, but so we can always find this A prime computable. Okay. Oh. Okay. So so one thing we proved is that the so in the sketch of the sketch of the sketch of the sketch, we needed Milliken's theorem. And so this result of ours shows that basically the instances of Milliken's theorems that we needed are arithmetically true. In other words, we color copies of Cantor space, we get basically substructures of Cantor space that look like Cantor space, which are also nicely colored with a number of colors, and that copy is arithmetic in the original. Okay. Okay, and it's not as long as they're looking at with some restrictions is not computably true, right? So you don't want to do just nodes. Okay, so if you're doing anything but nodes, is not computably true. And so it's open whether this is true for the various needed extensions of Milliken's theorem, right? So it's unclear, right? So this is where research is going on, is unclear for the click-free graph. There's an extension of Milliken's theorem that was needed. Is that provable in ACA or not? And also what's open still is what are the exact arithmetical bounds on the various instances of Milliken's theorem, right? So in other words, if I just look at, well, if I just look at coloring trees of height 3, what do I get out? Or 4, something like that. Okay. All right, so here is a conjecture that we proved actually in for the rationals and the Rado, and I conjecture that it remains true elsewhere too, right? And so we've looked at it. So there's a computable copy of A, such that for all B, there is this big Ramsey degree B L sub B, and a computable coloring of A with those number of colors, such that basically, well, this just says that hey, the first one says that we achieve this exact or big finite degree L sub B. Okay, and this is where it's the tightness or the types show up, is that in all copies of A prime of A, right, for all possible colors, right, there are many copies of A with that color, all right, from the coloring I have appearing. So in other words, I have some coloring of A, such that at any time I take a subcopy of A inside of A, every color appears. Okay, so this is like the types. Okay, this is types, and then there are many of these copies, right? Not just one, but there are many of these copies. Okay, and how they're dispersed about is going to be interesting, right? And so that's going to be important, how these copies appear in A prime. Okay, and so so I called it a computable coloring, but it's in some sense you're reading off the possible types in a language. Okay.
So you, I believe you've used this notation LB on the previous slide to have a definite meaning, but now you're
the same LB.
Is it
the same one?
So it
yeah.
will. So it's the sort of an effective tight bound,
right? I mean,
coincides with the actual tight bound.
It's a tight bound, because the tightness tells us that we can't go any better. All right, so it is a tight bound, right? So in other words, I'm claiming that the tightness is computably realized. Okay, you're welcome. And I have this coloring that realizes the tightness, right? And so then I want to claim about how I realize the tightness a little bit more later. Okay. Okay, so I'm going to shift now, and I want to talk about the naturals. And so what I want to do is I want to code in. So I'm going to go back here. I want to code in So where does this live? Okay, we know that it has to be arithmetic. Okay, and I want to show you that it basically, at least when b is greater than 3, that it has to code 0 prime. Okay, so it's going to be up in the arithmetical hierarchy. Okay, I'm not going to tell you exactly where it is, but it has to code 0 prime. Okay, now that's the case with Ramsey theorem, right? This is Ramsey's theorem on triples on triples, right? So any homogeneous set has to code 0 prime, right? So I want to repeat the proof of that and then try to use that proof in what I've been talking about. Okay, so how does the proof go? So Carl's coloring is you have a triple x, s, and t, and you basically color that triple 1 if k sub s restricted to s is equal to k sub t restricted to x. In other words, k doesn't change from x, from the initial segment from x, from s to t. Okay, and so so now we have a homogeneous set, okay, that has size 1. Okay, now I want to basically say that I could pick out whether z is in the halting set or not. So how do I do that? I pick a large x in H, right? There's going to be a large element, something bigger than z in that set. And then I pick a large s that basically is such that k is stabilized by stage s. Okay. And then there's a large t bigger than s in there, right? So that triple is colored 1, right? Okay. And so now if I'm going to kind of go through this, that triple is colored 1. And so I want to just rewrite this a little bit here. So if I have a triple of the substructure H, so just a substructure. So here we're just looking at sets, so the triples X, S, and T. I know that there's going to be a large T. There's going to be large T prime, S double prime, and T prime, such that basically, these triples are substructures of H. Okay. And I want to say that the triple, so this original triple is what I'll call largely extendable. And then these objects here are the large companion of the triple. Okay. And the second large companion tells me that the color has to be 1. That was the argument I did up here. Okay. The first large companion tells me that we can't have, so if it turns out that I have that I should have written this better. If these guys if the initial segments from S up to Z and T up to Z are the same, but they are different here, then there has to be some large T prime that witnesses that the color of this is 0. Okay. So the second companion tells me that I can't have clusters of triples, which give me the wrong result. Okay, so in other words, because I can't get clusters of these things. I always have to have, if I have a pair of triples, just a pair, I have a large extension. Okay, so basically what I have here is all the triples in H are colored 1, and I know that basically this gives me essentially the initial segment of what's going on Z, right? So actually what I wrote is okay, it's on Z. Okay, so I could pick out what happens on whether Z is in the halting set or not. Okay, so what I want to do is so here's what I want to claim here. So now I want to take this and move this to all the structures I've been talking about. Okay, so all of our structures are countable; they're computable, in fact. So there's a enumeration of these domains. So I gave you some kind of version of that. So I'm just going to enumerate these things, right? So in other words, I'm going to enumerate these in some way. So I have this d sub I. So in some sense, it could be the length of the node, right? But I'll let you do other ways you want to do it if you want. And now I'm going to say that when I look at this enumeration, I'm going to say something is large if the corresponding index is large. Okay. And now when B has size 3, I could use this notion of largeness to basically take a copy of B in A prime and ask when it's largely extendable and when we have these large extensions. Okay, so I'm just going to take this definition and translate it to the other structures, right, with that enumeration I've chosen. right? So I have a copy of B. So this is a subcopy of B. So I want to know, I want to find another copy. It looks the same, but the gaps between the elements is large. That's all I want. Same structure. Okay. And so here's a conjecture that's it's true. And it's true in A, and you have to prove it's true in all the copies, but so for all B, yeah. Yeah. So okay. So what I wrote is absolutely true. So for B in A, right? There are computably many appearances of A. Oh, this is written wrong. There we go. So for all B, for all of our A, there are computably many copies B in A prime. So A prime is just any computable substructure of A, right? Which are largely extendable. So in other words, in any, if I give you A, I can always find in any A prime, I could computably find lots of copies, right, in A prime where these structures appear largely extendable. Okay, so you have to prove that, and you could do that in a lot. Certainly, it's easy to do this in the original structure, A. Okay, and now, I mean, this is true. This is true. I mean, so but before I put this lesson, this is true because all these things are built up by this universal property. Okay, this is true. Okay, so this one is true because of the universal property. I always get those colorings. I can make the gaps large because if I have a fine, I can always extend by what I've talked about. But now what happens is, moreover, we could compute. I could actually basically find large companions with the same color as our original copy of A with respect to my coloring. This is saying that the large colorings, I could always find large companions that retain the same coloring with respect to my original coloring. Okay, so so the first part was true. I could always do that. But this next part says, hey, I have this coloring that's going on here, and my large companions have to have the same thing. So there's something to be proved here that I could always do this. Okay. So, and the first sentence is true. Well, if I wrote it right. The second one takes some work. The first one follows from the properties of the structures themselves. All right, so then now basically I claim that you could just basically code K when B is size 3 is once you have proven this for your particular structure. So it's a computable. So the C sub LB is a computable coloring that witnesses that L sub B copies must be realized in some all these copies have to be things. Okay. And well, look, I should say instead of each, I said many of these copies in B or computably many of these copies of B are largely extendable, preserving the ordering. Okay. Well, it's actually all of them in for the original structure. So now we could just take we could just take the product coloring and repeat Jacques's proof for any particular color. Fix the color, repeat the proof, you got it made. Okay. So, all right. So basically what I'm claiming here is that when you're trying to color a structure of size 3 or more, that the resulting copy A prime of A has to compute 0 prime. Okay. So, but now computing the exact bound still remains unknown in general, right? And so we didn't do that, right? But you could, you could, I mean, Carl has a copy that allows you to do this for, this was, does more than this, right? But that's still not done. Okay. So this answers some questions. I mean, so, okay. All right. All right, so the question is, what happens now in the remaining minutes? What happens when I look at substructures of size 2? So pairs. And it turns out there is a dichotomy that appears, right, between the Rado graph and the rationals. And what happens in general, I don't know. Okay. So, so the Rado graph, R is the Rado graph. So what we can do is there's take a coloring of all. So K2 is just basically edges. Okay. So we're coloring edges in the Rado graph. Fix some computable set. It turns out that there's a copy R prime of R where all the copies of R2 need just two colors and R prime doesn't compute C. So it's cone avoiding. All right. And it's done by forcing. Okay. So it's a separate, it's not using Milliken's theorem. It's a sort of forcing proof. So it can't code 0 prime. Okay. So it's weaker than ACA not. All right. So, a couple of comments here. So, we did explore how this statement is related to other statements in reverse math that are weaker than ACA not. And so you can look at a number of results. I'm not going to explore those here. Just not enough time. But I want to say something about I mean Milliken's. So here you have to, okay, because of the way you have to code. Well, you might be able to use Milliken's, but the standard proof of Milliken's, the instances of Milliken's theorems that you need to use, right, are not, they don't satisfy cone avoidance, right? So if you there's a standard proof that you could use to prove this, but the instances there that are in that standard proof of Milliken's theorems need they don't do cone avoidance. So you have to some different forcing proof here. So Ramsey's theorem from pairs also by Cetapit has cone avoidance, right? So it's similar to that. Oh, it's stronger. It's stronger, strictly stronger. Is that right? Well, I mean, I was asking Ludovic, but it's strictly stronger. So in some sense, yeah, it's strictly stronger. And so also I should point out here, so if we're looking at just pairs, if you look at Milliken's theorem, I didn't write it down, but there's also instances for nodes, trees of height 1, which is actually, so there's 2 levels, 3, so on, right? If you're just looking at 2 levels, that's also has cone avoidance, but it's also stronger than Ramsey's theorem for pairs, and implies, and it's that kind of implies them all. So that might be the yeah. Okay. So okay, so what happens to the rationals? Actually this cone avoidance doesn't happen for the rationals. So there's a coloring of pairs of rationals such that every subcopy of the rationals, so it's not so much of the rationals, where the pairs where the pairs are colored by exactly 2 colors computes K, right? So cone avoidance doesn't happen. Okay, so what goes on here that doesn't happen with the Rado graph? So what happens here is in this extended language that we have to talk about, the meet of 2 nodes exists, right? I mean, remember I told you that the 2 nodes, if I take a pair, how I coded it, they're going to be nodes in the tree. They're going to be in comparable levels. So their meet's going to exist. So in this structure, we have to include the meets of these objects in some sense. The language allows us to define the meets. So whether you include the meets or you put in the language, it's, however you want to do it, it's there. So basically what happens, a 2 type is actually a 3 type in some other language. Okay. And when you look in that language, in that larger language now, right? Right, that 3 type is largely extendable and has large things. So basically Carl's proof works on this extended type. Okay. So you don't know how many, so you have to be really careful what you get out of your structure. So you might have some hidden things in there. And so when that happens is unknown. Yeah, Paul.
How many colors do you need?
2.
Color compared. Color compared to rationals with every subcopy colored by
2 colors. Yeah, so I can't, the same proof that rationals, that I can't do it with 1 works here. right? Because the same, anytime I look in this tree, right, I always get, I mean, if I have a node, if I'm gonna have things to the right and things to the left, I'm always gonna have, I can always use that information to get what's going on. So I always have at least two colors, right? And so, right, so I have to have two colors. I mean, I'm not gonna prove it here today, but yes, does that make sense? Okay. So I guess the point here is that just because we have a two type initially, our language might actually provide us with a larger type. And so there might be more things going along right here. And outside of the rationals and Rados, we don't know what's happening, okay, for the other structures. Okay, so we don't know what occurs there. So it's likely they're more like the Rado than the rationals, but I don't know. So I want to go back to the Rado and see what happens here. I'm not going to go through this, but there is actually definable ordering on the rationals. I should be careful. Definable using the enumeration, right? Such that basically, if I look at if I take this ordering, I get something that's a dense linear order. Okay, so that without endpoints. All right. So I can define on the Rado graph, I could define nicely an ordering. But this ordering is not preserved. But subcopies of the Rado need not preserve this ordering. So if I take it, there are so in other words, what we said earlier, there are subcopies of this, okay, where there are subcopies R prime, where the ordering with the original R is not a dense linear order. Okay, so there's subtle things going on here. You just you use the passing number. So if you have the nodes here, you basically you take your Rado graph and you just enumerate it, and you just look at it. So if I have, let's call these Ri your Rado graph, and so then you'll have sigma I will be whether there's an edge from I to J. Yes. Yes. But if you remove pieces of that ordering, you need not preserve that ordering. Okay, that's it. Thank you.
Thank you, Peter.
Sure.
Any questions? Yeah, we had a lot of questions already during the talk. So
I like questions during the talk.
let's think. I see if there's any online. Yes, there is. No, that's not a question. Okay, let's thank Peter again. And after lunch at 1:30 with